So it's time for the mother of all gas laws. The ideal gas law equation is the best. PV equals nRT. We always call it pervnert. You could use it as a verb, like to pervnert something. It would mean to solve using the ideal gas law. This is the best gas law, and it's really the main one that's given to you in the AP packet. From pervnert, you can figure out all the other gas laws. So, like, for example, hiding in pervnert, I see PV. PV, that reminds me of Boyle's law, pressure times volume, or like P1V1 equals P2V2. If you're going to look at the relationship between pressure and volume, then the other variables stay the same. So the number of moles and the temperature would be constant. R is called the universal gas constant. There are different versions of R depending on what units you're given with your other data. So for example, here are the versions that are given in your AP packet. Now, be aware, there are a few different forms of R. Some of them are used in thermochemistry. The two that you'll want to use now are either 0.08206, and this would be atmospheres, liters per mole Kelvin. So this is the version that I would use when my pressure is in atmospheres. That also means that N stands for moles, not grams. So if you're given grams, you got to switch it to moles. Temperature does need to be in Kelvin. It always needs to be in Kelvin for gas laws. And volume needs to be in liters. And that's another one that people forget. You know, if we're collecting data in the lab, it's probably going to be in milliliters. And then I would need to change that to liters before I can use pervnert. So the main thing that I would watch out with this one, it's for atmospheres. The other one that's pretty common is 62.36. And this would be torr, liter per mole Kelvin. And a torr is the same as a millimeter mercury. And they'll tell you that in the packet as well. Not a bad idea before the gas test to look through this section of the AP packet so you know where to find the gas laws that are available, where to find these constants, what units are the constant. I would use all of these sig figs, so don't round it to whatever, 0.082. Use exactly what they give you. But it also does say that 1 atmosphere equals 760 millimeters mercury equals 760 torr. So those are given to you. These are going to be your choices for R, the gas constant, and they'll kind of dictate what units need to be used on the other variables. So again, we kind of mentioned that all the other little baby gas laws are hiding in pervnert. You've got your Boyle's law. Boyle's law. Your P1V1 equals P2V2. It's not given in the AP packet because they figure, well, heck, if we give them pervnert, they should know that pressure and volume are indirectly proportional. If I'm keeping, in the case of Boyle's law, if I'm keeping temperature and number of particles constant, then we can set these two conditions to equal each other. I would know Charles' law. Hiding in pervnert is V1 over T1 equals V2 over T2. If you rearrange this equation, if you do a little algebra, and you kind of condense all the variables that remain constant, you know, let's say I were to divide this by temperature, divide this by temperature. Oh yeah! Volume and temperature are indirectly proportional. Volume divided by temperature should equal a constant as long as I keep moles and pressure the same. The other one that's hiding in there is that relationship between pressure and temperature. P1 T1 equals P2 over T2. That's also kind of hiding in perv-nert. And I guess for kicks, I'll mention this. Here's sometimes you'll see this in first year chem. It's called the combined gas law. I'll write it down here. Combined gas law. Sometimes they'll use this, and it really is just P1 V1 over T1 equals P2 V2 over T2. Again, just another manipulation of perv-nert, assuming that you're keeping number of particles or moles constant. If N is constant, and obviously R, the gas constant, is constant, you could set something up like this and look at changing conditions of pressure, volume, and temperature. So again, these guys, yeah, you might run into them in maybe a multiple choice kind of question with manageable numbers. They're not given to you in the packet. They'll expect that you can figure it out by using perv-nert. Okay, so speaking of perv-nert, let's put it to work. So here we've got some diborane. Diborane sounds like it might be boring, but it's actually not. It's using like rocket fuels. It's pretty crazy and explosive and dangerous, and we don't have any. It has a pressure of 345 torr at negative 15 degrees Celsius and a volume of almost 3.5 liters. If conditions are changed so that the temperature is 36 degrees Celsius and the pressure is 468 torr, what will be the new volume? Okay, so there's a couple options here. We're looking at changing the temperature and the pressure. We want to know the new volume. They don't mention moles. So here are your options. You could do this. I'll do this first. If all you have in the AP packet is perv-nert, maybe this is where your mind would immediately draw. And you'd say, well, I don't know, let's plug in what we have. Here's my initial conditions. P, pressure, 345 torr. Volume, the initial volume, 3.48 liters. We don't know the amount of moles, but we could calculate moles. I'm going to use the second version of R, the 62.36 torr liter per mole Kelvin. And then again, temperature must be in Kelvin. So I'm at negative 15 degrees. I'm going to add 273, and that'll end up 258. Okay, so here might be one option, because again, all you have in the packet is perv-nert, and so you might say, well, I have all these initial conditions. I could solve this for moles. Moles, let's see here. We plug this in our calculator. I'm going to grab myself a little more room. Let's go 3 sig figs. Technically, this R value is a constant, so I'm not going to use that for significant figures. Everything else is about 3.0746 moles. Okay, so I'm assuming this is a closed container. They're not telling me otherwise. And with gas laws, we really can't do any kind of calculations if it's not a closed container. Okay, so if I know the amount of moles, and now I'm just going to change the conditions, we could just set up perv-nert a second time. So the second perv-nert, I've increased the pressure, 468 torr. I want to know the new volume, so I'll leave V as my variable. Now I know the moles, so I can say 0.0746 moles. I have the gas constant, which, to save me room, I'm just going to put 62.36. And then my temperature has also changed. 36 plus 273, 309 Kelvin. Okay, so let's plug this in and solve for volume. Volume 3.07 liters. Let's say that. Perfect arc's kind of nice for a situation like this where maybe you have opposing forces. Like, what if you were to increase the pressure? Well, that should decrease the volume. But yet I increase the temperature, and that should increase the volume. So you're like, well, I don't really know where the volume's going to end up. Yeah, you might want to calculate that one. Now, in the second one, again, I didn't put the units in on the gas constant R. You're probably going to want to do that. I know this is plug and chug, and it's like brutally easy for you, but you're going to want to put all the units in when you show your work. If you want any shot at partial credit, they have like 10 seconds to look at your work and make sure that you had it set up correctly. So putting the units in is going to help in that sense, and hopefully you're going to get it right anyways. But if you didn't, you want to show your work and your units. Now, if you're smart, which you are, maybe you would realize that, if this is a closed container, which we're assuming it is, I'm not given any data about moles, so I'm assuming that the moles must stay constant if it is a closed container. Well, if the moles stay constant, you could have just used this. You could have just used this combined gas law. And you've got your initial pressure, volume, temperature, and then your final conditions. And you could have solved for the final volume that way as well. But I set it up like this only because it might be like your first thought if you were solving this on an AP test, just because you won't necessarily have that combined gas law right at your fingertips.